Hello everyone, so we're continuing with the chapter Boolean algebra, and today we'll be discussing about logic gates. So what is logic gates? So a logic gate is a circuit with one or more input but only one output signal. So a gate is a digital circuit because it can take only values that is either high or low. So high represents 1 and low represents 0. So now we're discussing about the logic gates. So another method of simplifying the Boolean expression. Now after the Boolean expression has been simplified, now we use the logic gates to design the digital circuits. Right. So from here we can see how many inputs will be entered, and based on the type of gate you'll get the desired output like that. So the simplifying the Boolean expression helps to minimize the number of logic gates that will be used in designing the digital circuits, right? So the gates are of two types. First one is fundamental gate. So these are the basic gates which are not constructed from other gates. So that is the most basic gates from which other gates are formed. So we have the AND gate, OR gate, NOT gate, and in the derived gate, so these gates are derived from the fundamental gates. So we have NOR gate, NAND gate, XOR gate, and XNOR gate. So we shall see all of these gates one at a time. So now let's first discuss the fundamental gates and their types. So once again, fundamental gates are the basic gates which are not constructed from other gates. So the first one is the AND gate. Now the AND gate represents the multiplication gate. So this gate, it has to accept minimum 2 or more than that input signals, and it will produce only one output signal. So you can see that it will accept only it will accept two or more input values, that is like only two values, which is either 0 or 1. So you have 0 or 1. So when you have two values 0 or 1, only four possible combinations can be done, that is 0 0 0 1 1 0 and 1 1. So when you multiply that, when you multiply this, you are getting 0 0 0, and 1 into 1 is 1. So it acts like multiplication, and it will produce the output 1 when all the inputs are 1. So you can see that here, when x input value is 1, y is 1, so you get x into y, or x and y equals to 1. So this is the symbol, okay, and this is the truth table for AND gate. So you have to remember this symbol and this truth table at all times. All right. So next is OR gate. So now OR gate represents the addition gate. So here it also accepts two or more input signals, and it will produce only one output signal. So that is x and y is your input variable. So when the input values, that is 0 and 1, so the output will be x or y, or x plus y. So when it acts like addition and produces output when any of the input is 1. So in here, if any of the input is 1, 0 plus 1 1, 1 plus 0 1, 1 plus 1 1. Alright, so that is OR gate. So this is the symbol that represents the OR gate. Now next is the NOR gate, or NOT gate, or negation gate. So this gate has only one input signal and one output signal. As you can see in this symbolic diagram, it accepts only one value. So and then that value will be complemented. So if it is x 0, it will become 1. If 1 0. So this this triangular symbol and this circular, okay, represents the NOT gate. So it is also called as complement gate because it complements the input value, right? So the output is the complement of the input. All right. So now let's discuss the derived gates and their types. So derived gates are derived from the fundamental gates. So the first one is the NOR gate. So NOR gate is actually the combination of NOT gate and OR gate. So that's why here you have NO, that represents the NOT gate, and then OR gate. Okay, so this gate also has two or more input and produces only one output. Now in the case of this NOR gate, it produces output 1 when all the inputs are 0. So when all the inputs are 0, it will produce the output 1. As you can see in this truth table, x and y, okay, then x plus y the whole bar equals to, as you can see that when it is 0, both are 0, it produces 1. But when it is 0 1 or 1 0 or 1 1, the outputs are 0. So this is the symbol. As you can see that till here this is a OR gate, but when you put this circle in front of that OR gate symbol, this represents the NOT gate. Okay, so whenever in front of the symbol you have this small circle, remember that this is the symbol of the NOT gate. Okay, so the NOT gate means that when you place the value, when you input the value for x and y, suppose like 0 and 0, 0 and 0, right? Now OR gate, what it will do is that it will add the value, right? So that is x plus y. So x plus y, right? You just forget this one for the time being. So x plus y is 0 plus 0 is 0. But now you place the NOT gate before the output, right? So that is x plus y the whole bar. So what happens is that 0 plus 0 is 0, right? But because of this NOT gate, the 0 gets complemented to 1. Again here 0 and 1. So that is 0 plus 1 is 1. But because of this NOT gate, the 1 becomes 0. So you get the output 0. Similarly, 1 plus 1 is the output of OR gate. Output of OR gate 1 plus 1 is 1. But because of this NOT gate, the output of that becomes 0. Alright, so that's why NOT gate is written here after the OR gate. Alright, now next is NAND gate. Just like NOR gate, NAND gate is also the combination of AND and NOT. As you can see here, the symbol, this is the AND gate and this is the NOT gate. So here the NOT gate, it accepts 2 or more input but produces only one output. It produces output 1 when any of the input is 0. In the case of this, if any of the input is 0, it will produce 1. So you can see here 0 0 1, 0 1 1, 1 0 1 and 1 1 0, which is, suppose here is 0 and 0. AND gate means multiplication. 0 into 0 is 0. But because of this NOT gate, 0 turns to 1. And then 1 into 0 is 0. But because of this NOT gate, 0 turns into 1. And in the case of 1 into 1 is 1. But because of this NOT gate, 1 changes to 0. Right? So you have to remember this diagram, okay? And this is a truth table also. So this is so you can see that the NOT gate, the where there is NOT, it is represented by this bar. So x and y the whole bar. Now XOR or exclusive OR, right? So this is like a hybrid gate. Okay, so combination of the fundamental, the derived gate. Right, the fundamental and derived gate, as you can see here, it produces output 1 when either one of the input is 1 or odd input pairs. Right, so if any one of the input values, it does not match, suppose x is 1, y is 0, or x is 0, y is 1, then in that case the output will be 1. So this XOR, exclusive OR, in the truth table it is represented by this plus and then these circles. Okay, so when both the inputs are same, output is 0. So you can see here 0 0 0 and 1 1 is 0, which is represented by this symbol. Right, so you can see, so you try to remember this symbol, right? So this is the hybrid gate, which is the combination of fundamental gate and then the derived gate. All right, so next you have is the XNOR gate. So this gate is the complement of XOR gate. So what we have just seen, this XOR gate, exclusive OR gate, and this XNOR is just the opposite or the complement of the XOR gate. So it is actually the combination of XOR and NOT gate. As you can see in this here, you have the NOT. This represents the NOT, right? The only thing that is changed in this diagram is this small circle at the front. So this represents the NOT gate, and you can see in the truth table also the circle is there and then the AND operator. So it will produce 1 when both the input is same or even input pairs. So as you can see in this diagram, when the both the input values is 0 0 or 1 1 same, then 1 is produced. But in the case of when it is not same, then 0 is produced, right? So before we go on to the truth table exercises, okay, go through all of these logic gates, okay, try to understand the difference between the logic gates, and then memorize the symbols well, okay, because you'll be using these symbols, and then the truth tables a lot on this. So this is also very important. All right.